talk that emerging technology is that interesting career. Either that or I've got very limited imagination. So the first question that I usually get asked is, why have an emerging technology group at all? On that, we're actually drawing on some of the stuff that I did in my marketing days, which was that if you look at the typical marketing textbook diagram of what happens with a new technology, is that it starts off with a small number of advocates, it becomes mainstream business. After a while, it gets replaced by something else, and it dies off into being replaced by another technology. So that's all well and good, but really what was happening, and there's a guy called Jeff Moore out in California who pointed out, actually, for high technology, what happens is that there's a gap. And what happens, he called it the chasm, is that there's a degree of miscommunication and misunderstanding between the left-hand side of this and the right-hand side, which is because you've got different groups of people. You've got the technologists on the left-hand side who speak a different language to the mainstream business people, and the mainstream business people just don't understand the technology that's being put on there. So he called this thing the chasm, and what he advocated was that we needed to find ways of actually crossing this chasm. And one of the ways that he postulated you needed to do this was to put together mixed teams of technologists and business people, get them working on problems, producing proof of concepts or first of a kind, that enabled industry then to see the benefits and actually apply them correctly. So, it's another way of stating the sort of like Gartner Hype Curve. It's trying to make sure that you don't fall into that chocolate solution where, because of miscommunication, you don't really understand the technology and how it comes together. So, that's why we've got a team together, and that's why I've got a emerging technology group within the UK. And what I'll do is just describe really how we work. So, first thing is, in terms of emerging technology, is actually being able to understand what technology is coming downstream. And to do that, we get involved and take advantage of a lot of work that happens around forecasting. I've just put up some of the ones that are IBM specific, but different companies have different approaches. And one of the things that I'm very keen to do, and I do a lot of, is talking to similar people in the different companies to swap ideas as to what we think is going to become correct and what's going to become a real technology. Now, that's great because as an industry we need to make sure that we're following the trends and being able to predict them and make sure we've got the products in place to try and do it. There is a slight worry with a lot of these things that by forecasting and looking at gaps and filling in those gaps, you actually start to become channeled, but hopefully some of the forecasting, because they're done quickly enough, to stop you doing that. So just I'll mention a couple of them. The Global Technology Outlook is IBM's approach to really trying to understand what's happening in the world and what's going to happen in the next 10-year time frame. And to explain how that happens, every year a call goes out to the R&D community, gives you bright ideas, gives you thoughts, what's going to make a difference in the IT industry in 10 years' time. A committee gets put in place. That committee works those ideas through to sort of like the implications. And importantly, at the end of that group, it gets completely disbanded, a new group gets put in place to try and take their ideas forward. And we're just going through that process now at the moment, and I've got 2 ideas under consideration that will be fitting into that Global Technology Outlook that will come out this year. So, I've got this idea on what we're trying to do. Typically what I tend to do is try and break them up into a couple of categories. One I'm calling business as usual. So these are the things that are the underlying trends. Moore's Law's been going on for many years, it's going to continue for many years. What's going to make an impact because of that? Metcalfe's law is slightly more esoteric, but really what it's saying is that the value of the network increases as the number of nodes get onto that network. And so with both of those things, one of the things that we do a lot of is really trying to address business cases that have been put in place, because some business cases that weren't feasible a few years ago, if you revisit them because the underlying increases in technology actually become feasible. So, we go back to some of our business partners and say to them, look, at this point, this cost benefit analysis didn't work out correctly, but if we were to readdress the whole business case, we can actually improve it. So that's the sort of underlying principle we get. And there are other things that feed into this as well as the different Moore's and Metcalfe's law. Just the general increase in data. This is one particular forecast. There are other ones around there, but we're really looking at huge amounts of data. Interesting enough, a huge thing that comes out of this graph here is a lot of the data is unstructured data. So typically most of the one-normal architectures, most of the systems built around that are very good at handling structured data, but they struggle with unstructured data, and there are some implications that come back from that. So the next things are really just sort of like selected highlights I've picked out the last couple of years in terms of the forecast, but data curation, huge issue. I mean, a personal anecdote is that I'm that old that when I was looking at the ozone layer in the late 80s, I missed out getting a Nobel Prize because I never spotted the fact there was an ozone hole. Now, as it turned out, data curation did for me because at that point the understanding around the ozone layer was that it was constant. So somebody's written a rule into the data to filter it such that if the data wasn't constant, throw it out. So I only ever saw constant data because somebody had written that rule in. And that really brought it home to me is that you need to understand what's happening with the data. And typically, about 80% of the cost associated with a big data project goes into actually data curation and trying to understand how best to use that sort of data. Not only do we have the issues in terms of data curation, data at the edge is becoming increasingly important. We are now all addicted to smartphone usage, and all that data at the moment is a lot of it residing on the smartphone and neither getting back into enterprise systems. So we're doing a lot of work around understanding how you can actually put together systems that take account of data at the edge. And I guess the final one is that we're already in an age where data on the cloud is equaling the amount of data that's sat around on centralized servers. So cloud, whether you like it or not, is going to become the de facto way, if for no other reason than most of the industry's R&D money is being focused around cloud-based systems. So all of those things are sort of like what I was calling business as usual. And really what it enables you to do is to do what we always used to do in terms of this left-hand side is being very good at automating the world. Faster, better, cheaper enables us to do things that we weren't able to do a long while ago. And that really is what we're seeing with this business as usual frame. The interesting thing for me and where I'm really getting excited is that we're moving away from that view of the environment into one where we're trying to understand the world. And to do that, it requires a whole new range of technologies, a whole new range of activities to make sure that we can actually get value out of all this data and all this stuff that's put in place. So machine learning is obviously key, but equally important, metadata analysis around video data, speech analytics, all of these different things that are important. And clearly as an IBM, using tools such as our Watson capabilities to make sure that we can actually get some benefit out of the activities going on. So that dimension has been brought about by us looking at really what I'm calling a whole range of disruptive technologies. And I'll just go through a few of them and what we're really trying to do with some of them as we're going forward. Cognitive key, and that's an area I'll look at. Neuromorphic processing, again, looking at sensory data. Biometrics, clearly now becoming a huge activity. Again, going back when I started off looking at biometrics, nobody was interested in using it as a security mechanism because the public perception at that point was that only criminals had their fingerprints taken. Now, having had it launched on things such as the iPhone, it's becoming a de facto route for using security on systems. Not only fingerprints, we've got iris, we've got face recognition, all of these technologies being used as a way of making a much easier sign-on for a whole bunch of applications. And I guess, just a quick show of, how many people use biometrics in terms of unlocking their phones or devices or anything like that? Yeah, it's interesting. I asked that same question about 4 or 5 years ago before Apple launched, and with their fingerprint scanner, and no one did it. So, it's just a way that the industry is picking it up. And we've done quite a few projects in this space, and I'll show you a few of them as it goes through. wetware, you've heard of hardware, software, but the idea of people being used as part of the system is something that's important, and we've been doing some work around that. And finally, just when you thought it couldn't get complicated enough, now let's look at quantum computing and how that's going to have an impact. So the team that I've got at Hursley, which is half of my team, works on applying these technologies to real-world customer problems. So looking at them in turn, if we start off with the disruptive technologies, I mean, if you think about what we used to do with grand challenges in IBM, the idea was to try and stress the research department by giving them something that looked impossible and seeing how they could go around and solve it. Now, the one that kicked off and got the most publicity about this was in the late 90s, where we launched a challenge against one of the chess grandmasters, Gary Kasparov, in terms of could we beat him at playing chess. Now, at the time, it looked sort of like, again, debatable whether we could do that, but we put together a system, we put that in place, we played him, we won. We claimed we cheated, but that's part of the course. My impacting memory is that last year I shared a platform with Gary Kasparov, and after 20 years it still hurts to be lost to us. He kept saying, when are you going to give me a rematch? But it's, for me, having done it, it was less interesting a challenge in some respects, because chess is a game with a large number of moves, potential moves, but they're finite and all follows set rules. So if we hadn't beaten in late 90s, I think we'd have said, okay, 2 or 3 years downstream, the underlying performance would have got better, we'd have been able to think further ahead, we'd have beaten him. So in that instance, for me, it was a case of when, not if, we would actually beat him. But the lesson that I took away from that was that the processing power that we used on that system, which at the time was a state-of-the-art mainframe, with a huge team of programmers behind it, was impressive. But 7 years later, we rolled out that same processing power as the PlayStation 3 chip. So something went from state-of-the-art mainframe sort of systems into every teenager's bedroom in the space of about 7 years. So when we set ourselves these grand challenges, that's the sort of timescale we're talking about in terms of moving from research into adoption. When we look at this one here, the Watson challenge, we did that in 2011. So we're now at that 7-year time frame, and we're starting to see that we're applying the same sort of technologies across a whole range of systems. So that's very important for us in terms of what we're trying to do and how we're trying to pull technologies through. The Watson challenge for me was much more exciting though. And the reason is that what we were trying to do was use technology to play humans at a very human-oriented game. Language is very bad to draw rules around, because if you don't understand the context, you don't know what things are being put about. So, for example, if I work for Boeing and I put in plane into search engine, I want to get in, stuff about aircraft. I don't want to get woodworking tools. But it's the same sounding word, the same way that the thing's set up. How do you actually sort of like differentiate those things? So, all credit to them. I was not involved in Watson in terms of putting it in place, and all credit to the team that did that. It was a stunning technical performance, and it showed that we could actually start to build systems that can work in that space of natural language understanding and trying to put that in place. So that was important. The other thing I think was important was that we called it cognitive computing, not artificial intelligence, because for me, artificial intelligence comes with a whole set of baggage that we're not really tackling at the moment. For me, artificial intelligence is all about trying to understand sensory data, and at the moment we're not able to do that. Until we started to launch, and we're not the only ones, but this is our version of it, chips that can actually understand sensory data, that are built the same way the brain is built, with a whole series of neurons that are connected by multiple synapses to other neurons that enable you to use spiking algorithms and all the different ways you can actually understand sensory data to try and pick things up and understand what's coming out of it. So at the moment we're doing our first projects around neuromorphic processing. The chip that we've got at the moment is the True North chip. It's got about 1 million neurons with 256 million synapses, and enables it to actually do applications around sensory data. So this is just one of the standard tests that people are doing. We've shown the system pictures of people on bicycles. We've shown people just walking by themselves. We've shown cars, and the system enables you to, in real time, frame by frame, do a classification of these things coming across. Have you noticed just on the left-hand side now, there's something that's flickering between green and purple? That's actually somebody on a skateboard. And the reason that it's unsure about it is it's never quite sure how to classify it. It's either saying it's a person or it's a bicycle, it's not quite sure. By building a feedback loop into it, saying that this is something new because I can't quite understand it, we're able then to start getting a system that can learn for itself and actually pick up the fact that this is a new category and ask for clarification as to how they should classify it. So all those things build up into, like I say, a whole series of systems and capabilities that will now allow us to look at doing analytics around sensory data. And that, I think, is going to be an important development. I mentioned biometrics and say how we've seen those developing. Let's show a clip.
Hello, Mr. Yakamoto. Welcome back to the Gap. How does assorted tank tops work out for you?
Mr. Yakamoto.
So again, quick quiz. Anybody know what that film is?
Minority Report, is it?
Yeah, it is. And as you see, somebody comes into a shop, they do iris recognition, they understand who that person is, and they tailor the advert for them. Now, we were asked by a major retailer to produce that same capability. Now, if you know the film, we were able to produce that with a couple of differences. One was that you didn't get that flash of light, so you didn't know that anything was going on. And the other one was we couldn't swap people's eyeballs. But again, that was down to us, not down to the technology. And similarly, when we go on, for those of you in IBM, you won't recognise this, but this is a business class seat that we always sit in the back of a plane. But one of the things that we were asked by an airline was, could we enhance the business class experience by understanding how people were in terms of their biorhythms, so that they could better tailor the settings, such as they got fed when they needed to, help to sleep when they wanted, and we could build all these things into a profile around them. Now we did that by actually instrumenting up the seat such that when you sat in it, we got a measure of people's heart rate, we got an idea of their anxiety states, we could profile how they were feeling, and we could try and understand how best to do it. Now, the technical challenge was solved by a couple of sensors that say literally just sit in a seat and measures all this sort of stuff. The issues we had with that one then were, what do we actually do with this data, and how do we actually make sure that we don't get into any kind of data protection issues? Because clearly, if you can spot that somebody's in a distressed state, and yet you allow them to fly, how do you actually do that? Now, what we actually did was that we built an app that somebody can collect their data directly, such that the airline never holds the data, the seat just transmits a direct to that person's app, and the liability shifts to them in terms of how they're feeling and how they're put into these sort of situations. So all of these show how we can actually personalise and make an experience much more relevant to an individual that's coming across. And I mentioned wetware, and let me just show you this. We've got a program in the UK called Bang Goes the Theory, and it's basically a scientific education setup. And we had a request from them to help them with a challenge they wanted to do, which was to drive a cab around Piccadilly Circus with just using thought patterns. So thinking left, thinking right, being able to sort of like steer this thing across. Typically the IBM lawyers took one look at this and said no. However, they did let us do it on Sandspot Raceway, where it was fairly able to actually do it safely. So I'll just show you the ending of this thing here.
Will our brains be up to the challenge?
Go!
Yes, I've done it! The first ever brain-controlled taxi.
Now we're seeing a whole lot of stuff about autonomous cars and things like that happening. This was just another approach we tried to do. Really just trying to understand how we can best take advantage of things around people's sort of like personality. It's a whole series of things can be sparked off by this sort of setup. And we're already seeing that it's difficult now to differentiate between machine-generated content and people-generated content, particularly when we're doing sort of like social media analytics and things like that. And this is just another indication of how people are getting much more aligned to the technologies that are coming through. Hopefully, as I said, that gives the indication of the capability. I've got to confess though, I did do some editing here because at this point the taxi veered off and took out the barrier, but I thought I'd not show you that one. The next one that I wanted to look at was quantum. And this is one that, for me, is really proven to be quite a challenge. I mean, I think that diagram is quite useful because everybody's saying quantum's going to be wonderful, it's going to solve all the problems, but really it's not. It's going to be very good at solving some things that are probably not solvable with classical computing. It's not going to be as good as some other things in terms of classical computing, and some that both can do. So please, if people talk about quantum, we're starting to look at this, we're trying to do work with it, but it's not the answer to everything. But it is going to be an answer to some problems that typically have been intractable. So scheduling problems, resourcing problems, all of those things are, RSA decryption sort of algorithm, all the sort of things that quantum can do very easily and a lot better than classical systems. But for some things, it's not going to be as good. Really, all I wanted to do on this one though was to highlight the fact that there's a website here. If you want to start playing around with quantum, you can go on and start to do stuff in terms of understanding it and doing some work on it and signing up for particular programs to do some activity with it. So I'll leave the slides and there's a link in there that you can actually start to pick up on. In terms of where we are at the moment, I believe they've launched a 20 qubit system that's freely accessible across this interface. We've got a 50 qubit simulator that's out there that doesn't use huge amounts of memory, it's terabytes rather than petabytes of data needed to drive this thing. So hopefully we can build up quite a bit of an ecosystem around there. But we're at early days, and one of the things that I always thought was quite instructive was looking at the quantum computer now and looking at where a classical computer was in the 40s. You can see a huge amount of parallels in terms of how these things look. But it's probably an indication of where we are in terms of seeing this thing across. So that's really what my team at Hersley is doing. I said I also wanted to mention what we're doing at the Hartree Centre. The Hartree Centre is launched as a part of what's in the UK is known as the Science and Technology Facilities Council. It's a UK-funded group that is set up to make high-performance computing accessible to a whole range of academic and, with the Hartree Centre, industrial partners. And the reason behind this is that a lot of people have work and computing power that needs high-performance computing, but quite often they don't have access to it. And similarly, particularly in industry, not only do they not have access to it, they don't have the people who've got the skills to actually write up some of the stuff that's needed. So the Hartree Centre was set up to try and solve this setup. It's really all about providing, say, industry a route into this stuff without having a huge entry barrier. It's very difficult to build a business case as an industrial partner to say, I need to go out and spend a huge amount of money on a high-performance computer without the capability of demonstrating why you actually need this sort of setup. So customers can come in, they can understand what we're trying to do, and they can show results that can enable them either to continue on working with the Hartree Centre or to branch out and build their own systems, knowing that they've got a sound basis to try and work across. It's all about transforming UK competitiveness, and it's the sort of problems that you would understand in terms of what we're trying to look at. So it's modelling, it's simulation, it's understanding how we do digital twinning, all of those things are put in place. In terms of where we're at, the The Hartree Centre was set up and it's been built on since 2015. It was extended to have a connection between who are government employees and 50 staff there and IBMers. So we brought an IBM team in to try and do that. Physically, they're located in Daresbury, UK, which is close to Manchester. And that's a group that is set up specifically to work with clients on building these first-of-a-kind prototype type systems. As the thing becomes commercial, it can move off into different spaces, but in that early stage in terms of emerging technology, bridging between research and the setup, it's all about trying to capture with these people a whole series of activities and making sure that they're relevant to the work that's going on. There's a whole set of machineries that we've got. We've got Intel platforms, we've got IBM data-centric platforms, and we've got a whole range of emerging tech that's put in place set up here. No preference for the platform, it's really a case of trying to understand what the problem is and then putting it onto the best platform for trying to make the best use out of it. Clearly, the IBM team is based around the data-centric platforms and they do a lot of work on that space, and that's some of the stuff that we are showing now. But, we've got huge platforms.
Actually, sorry, can I ask a question? Our first talk this morning was from Christoph Dubach here, and he has this lift system that he's developing with his team at the University of Edinburgh. And that sort of key idea is to make it easy to program across a variety of heterogeneous systems with different types of GPUs or FPGAs. I just wondered the degree on that previous slide to which you're seeing programming issues because you had a really wide range of machines there.
Yeah, what we've been trying to do is to start off with understanding where the problem space is and trying to match it to the machinery that we've got. So in some instances, we're saying that clearly if it's more a data-centric thing, and particular because at the moment we're on Power 8, but we're going to be moving to Power 9. Once we've actually can take advantage of some of the inbuilt capabilities of those sort of platforms, certain problems will naturally lend themselves to actually working on that space there. And so, we've got Paragon and Panther R2 systems, but up in Edinburgh they've got other STFC systems, Archer is one of them, and others looking to be replaced. There's other platforms here down at Daresbury, but it's more a case of trying to pick the problem space and target it to the machine that gets the most advantage of it, rather than moving stuff or building stuff that can work across it. I guess it's really horses for courses is what we're trying to do, is pitch the thing at the correct platform. We could take something that works quite happily on the data-centric platform and try and code it to work across an Intel platform, but it's likely to be less efficient, and so we don't really have much of a desire to try and do that. Clearly, if somebody wants to do that, then that's okay, but it's much more trying to target the platform and then set the system up against it to work correctly. So that's really how we're set up. Rather than trying to make one platform or one system that run across all platforms, it's taking advantage of each individual platform and targeting across from that. So as I said, Paragon and Panther are two main systems. Again, there's more information on the slides, but I'm not expecting to read all this stuff, but they're all set up to try and do it. And then, we've got their own sort of like network system put in place here. We have got supporting facilities that back across all of the different systems. So a lot of the data architecture is built around the various platforms, but we can move stuff in and out across the different systems as and when it's needed. And say there's nothing to stop you targeting other machines, but we're just saying let's say pick the best machine for the work that we're trying to do. In terms of the UK, this thing is known as IROR, Innovation Return on Research, and it's making sure that we get a good return from the government funds putting into this sort of thing here. So it was a big investment. We're running up until 2020, and we're starting to show returns on that setup in terms of companies coming in saying that they've enabled us to do a whole load of work that we weren't able to do. And it's all open. So I say companies coming in, work with us, we pass on the results to them, and we're also working at an industry sector level, such that we showcase the results of things that we've done for a particular company such that the rest of the industry can understand what's happened and take advantage of it. Typically, the sort of problems that we're looking at span across a whole range of different capabilities. There are some that are enabling technologies. So, we're looking at cybersecurity in some novel ways. We're doing some work around a technology called fully homomorphic encryption, which is a way of actually being able to articulate a problem space such that you can query an encrypted database with an encrypted query, bring back an encrypted result, such that the person who holds the data doesn't know what the query was or what the result went back, and the person who is making the query never understands what else is in the database, which for a certain number of use cases, particularly when we're starting to do stuff that is commercially sensitive, is clearly an important element. So that's in the enabling technologies stream that underpins all these things. But the areas we're looking at, chemistry, life sciences, and sort of like engineering, all of these sort of things are challenging in terms of the quantum computing that we've got. So some of the projects we're working at, Unilever, looking at computer-aided formulation. Currently at the moment, they spend a large amount of money on chemistry, wet chemistry sort of results. So in that instance, what's happening is that they are actually building stuff and testing it and finding out that chemicals will work with a huge amount of cost, large amount of delay. But for some reason that's got all through, never mind. But what we're about is trying to produce a digital twin of this sort of setup, such that we can model a formulation before it actually becomes a physical chemistry experiment, such that they can cut down their time, because we can run things virtually much quicker than they do an experiment, but also we can save costs because it's much more expensive to try and do that. And we're looking at simulations of different solutions, how they mix together, building simulations around it. And then the final element in terms of what we're trying to do is look at simulations with machine learning, so to try and understand what's been done before to try and work set up on there. Thirdly, what we're trying to do is to get high performance computing to work smart, not hard. But we're looking, the measure that we're trying to set ourselves is that we're using a third of the calculations to achieve 4 orders of magnitude resolution increase. So that's the metric that we're setting ourselves in terms of trying to build this setup up. So that was a chemistry one. We're also looking at life sciences. One particular area we're looking at is crop protection. And in that instance, what we've done is that we're building around a particular technology we're calling PAIRS, which is a geospatial database, producing a whole series of modeling systems on top of that to enable us to do very high resolution modeling of pest-bearing insects. So when coupled with a whole range of capabilities for doing modeling and mapping, what we're able to do is to produce forecasts such as this, such that we can actually plot using not only the real measurements, but also using social media inputs. So, if a farmer particularly reported a particular kind of infestation, we can build that into the model to help tune and correct it. But the reason why this is important is that if we can understand where the insects are going, we can understand where the diseases are going, and we can protect the crops ahead of time by doing the spraying in such a space. Now, there's an estimation being done, which is that we can actually improve the crop yield, but also decrease the costs and also decrease the use of insecticides by doing this degree of modelling. So typically, a farmer is cautious, will spray if he thinks there's an indication that something's coming. It will provide a better forecast. There'll be less spraying, less cost, less impact on the environment, but also hopefully an increased yield because we're actually targeting the setup that's being done for that there. I mentioned digital twinning. Now some of the stuff we're looking at companies such as Dyson. For them, they're all about making more efficient fans and motors around those sorts of products that they have, which is typically around either vacuums, hair dryers, but also they're now starting to look at producing cars. So they want to be able to quickly mock up and modify some of the codes that they've got. We're also looking at certain things such as aerospace applications and understanding how those things can come about. Now, for me, it's this sort of thing I think it's got a huge amount of potential because we're able to model not only the business as usual sort of stuff, how to improve the fan blade, but we can also quickly model disruptive sort of technologies. And I don't know if you noticed that probably about 10, 15 years ago, aircraft, passenger aircraft had flat wings. Now they've all got winglets attached on the end that are effectively disruptive technology. Now, the previous simulations that have been done were all about making a better flat wing. What we're about is trying to understand, can we do different tweaks around the system to actually get better capability and flow going through the system. And all that stuff comes together in, I say, chemical and engineering applications. We're looking at oil and gas, we're looking at food industry. The last one is an interesting one, effluent dispersion and wastewater. Now, I've got to actually do some work on this fact, but I was told by somebody who, I'll not name in case it's wrong, that the UK spends best part of 20% of energy associated with wastewater treatment. Really what that's all about is that it's a Victorian type system which is heavily involved, mass pumps, moving water around, doing a lot of work around it. If we can actually build systems around using IoT sensors again to sort of like put the emphasis on getting the correct amount of treatment rather than just over-engineering systems, get a huge amount in there, we can make huge numbers of savings. So all of these things are applications we're looking at. If I've just put up here, there's a whole range of customers that we're working at. Some of them are further ahead than others. Unilever are probably the one that's most advanced, but Dyson, Syngenta, GSK, all of these companies are working with us. So the final bit I just want to do was just go about, how I see, what we're doing is different and why it needs different skill sets. A lot of problems that we find with emerging tech space is that it's actually, we're working in an unknown space. There is no training you can go on this sort of setup. There is no problems that you can build around. So key skills that we're looking for is problem solving, people are collaborative, multidisciplinary, because we're going to have to work across a whole range of different applications, and naturally enough, 1980s. And the final quote is one that I got from one of our customers that initially I thought was an insult, and then he said, well, you guys aren't professional, you just gifted amateurs. But actually he meant it as a compliment, and the reason he did was that our thinking wasn't channeled around traditional lines. We were able to sort of like bridge across different applications and pick up the real trends that came across. And that, to us, means we need a whole different set of roles that we're trying to bring people in. So we've got a large number of data scientists, we've got a lot of accounts developers, and designers. Design being key. You're working with customers, being able to articulate their problems and produce solutions against them is really important. And that's, I think for me, would be one of the lessons, and certainly one of the areas that we're starting to do a lot more around recruitment. So I want to finish up on time, because unfortunately I can't be around for the panel discussions and leave some time for questions. So I'll just say thank you. And particularly say thank you to people whose slides I've stolen. That's come from the STFC and IBM research staff. So if they're wrong, it's my fault. If they're good, it's probably somebody else's fault. So at that point, I'll turn over to any questions.
Thank you.
Yeah.
So you mentioned when you were talking about the chess stuff that you knew it was a question of when and not if.
Yeah.
How would you characterize two of the emerging technologies? One is roads being shared by human drivers and autonomous, and the second one, quantum computing.
I think the first one is really interesting, and I think it's probably going to become more of an issue for society rather than technology. The reason I say that is that, you know, we've just seen there's a large amount of press coverage about, you know, a car that unfortunately, you know, had tragically hit somebody and killed them. Now, you know, we're putting different standards on the technology than we're putting on the people who drive them. You know, people drive when intoxicated, people drive when under the influence of drugs and have accidents. And we don't therefore stop everybody from driving on the grounds that you know, these things happen. But with the, you know, the machinery, we're saying, well, unless it's absolutely safe, then you know, we're not going to let it fly. Now, you know, the analogous setup is probably, you know, air travel. You know, everybody travels on aircraft. Aircraft sometimes crash. Sometimes that is down to human error. Sometimes that's down to some kind of technical challenge. And we need to get that balance right. But I think it's driving me thinking that technology is going to improve, but there has to be a point at which society is comfortable that we're able to adopt that sort of setup. So that was the first one. What was the second question?
Quantum.
Yeah, quantum. I think it's going to come quicker than most of the predictions. I started talking about quantum about a year or so back, and the estimates for how many qubits we have in place were very cautious, and I think they've all been, all the estimates I originally had have all been exceeded in terms of how many we've got on there. And the other thing is that the emphasis is not only on the number of qubits, it's the quantum volume or the error associated with those qubits, because I think a lot of the early indications didn't take account of the errors that were brought in, and you can throw a huge number of qubits together if you're not too fussed about the errors. The problem is that doesn't give you the increase in scalability that you're looking for. So I think the theoretical maximum is, you know, doubling performance every bit you allow onto these sort of systems. But if you have errors associated with those qubits as you put them in place, then that can derail some of those predictions. But my estimate on that one is I would see it happening quicker than most of the predictions are out there, because I think, you know, it's starting to snowball with the number of qubits being put out there, and they're all proving quite accurate systems as well.
So when you say happening quicker than estimated, you're thinking of these things, clusters being available and actually being used by independent.
Yeah, you know, I think one of the interesting things, the approach that IBM took was to open up that system to build up an ecosystem of people who are skilled with using quantum, and that I think is going to be a really good approach for the industry, because, you know, people can get into this thing with no you know, need to invest in the capability. They can just log in across the cloud, build their code, run it on the systems, and come back with results. So, and I think that ecosystem will probably drive development, and that's why I think it'll probably happen quicker than if it was locked in and proprietary.
I thought your comments about biometrics were very interesting. And I just wondered, what do you think in the future, or with the way technology is developing, do you think it would be possible to kind of opt out of giving your biometric data, or will we all wear paper bags on our heads in future? Or how do you see it developing in terms of, you know, people who maybe don't want to share their biometric data?
The interesting thing for me is that this is now becoming consumer pull. You know, people are using, I mean, if you look at the take-up on things such as, you know, fingerprint scanners on Apple, you know, the iPhone is, de facto is becoming, people are using the fingerprint scanner. It's an interesting setup. I mean, the iPhone scanner is not particularly good. I don't mean that in a derogatory fashion. It's quite old technology. It doesn't detect aliveness, so, you know, it's potentially more easily spoofed. But you know, for what people are using it, I think it's been proved to be a huge boost. The other thing I think we're going to see is that we're going to move from a security domain that's black and white. By that, what I mean is that, you know, we have to, you know, uniquely identify who we are, and we have to be 100% sure that that's not happening when you put them in it, to a sort of like a risk-based approach. where we're going to say, you know, for a particular application, say, and we've been calling this frictionless identification. For a particular application, say, checking my bank balance. You know, if I'm just out on my own, you know, then you know, checking my bank balance, there's no real risk. I might have a relatively low level of security to try and do that. But if I want to transfer the contents of my bank account somewhere else, then I might not just have to do a password, I might have to give a fingerprint, I might have to give them a password. And the machine, like the iPhone, might have to be in a particular location, and verify itself to be in a particular location to allow me to do it. So, you know, if I'm at home and it's me giving the fingerprint and I'm putting a password, then we're pretty sure it's correct. It could be spoofed, but it's a risk-reward sort of setup that's on there. So I think we're going to see a range of security, so there's sort of like grey area of security rather than a black and white sort of setup. And I think biometrics is a huge tool to play in that space. Yes, people should be able to opt out, and some people will opt out, but the capability of the systems themselves are going to show that, you know, a lot of what we would count as data that wasn't suitable for biometrics. So, you know, CCTV coverage, you know, huge numbers of crowds and things like that. You may think that initially, you know, the biometric capability isn't capable of picking up some of these sort of like identifications. But I think the capability underlying it is getting better and better. So it is going to be a constant re-evaluation of what the security and privacy restrictions are and how you tie into them. GDPR is going into force next month, and that's starting to prove challenging for biometric but also non-biometric